So let's look at an example where we have to do some extra work. Find a fundamental set of real valued solutions, that's important, for the system dx dt equals x minus y, dy dt equals 5x minus 3y. So therefore our matrix A is 1, -1, 5, -3, and when we want to find the eigenvalues of that matrix, we just subtract lambda from each of the terms in the main diagonal. That gives us A minus lambda I, and then we find the determinant of that. Since it's 2 by 2, it should be pretty easy. So lambda squared plus 3 lambda minus 2 lambda, or minus 1 lambda, so plus 2 lambda, and then minus 3, and then plus 5. So lambda squared plus 2 lambda plus 2 equals 0, and using the quadratic formula, which I'm sure you've all memorized by now, lambda simplifies as -1 plus I and -1 minus I. You should work that out if you don't understand it, but we've got our imaginary eigenvalues. Oh, that makes things harder. Yeah, imaginary eigenvalues, we're stuck with that. But now what we want to do is find an eigenvector associated with our imaginary eigenvalue. Yeah, that's going to be tough here. So that means we need to solve the equation for lambda equal, I just chose to use this one, -1 minus I, and we solve the equation A minus lambda I times vector k equals 0 using an augmented matrix, and this is 1 minus lambda, that's 1 minus -1 minus I, and this is -3 minus -1 minus I. Simplifying that, the augmented matrix is 2 plus I, -1, 0, 5, -2 minus I, 0. See this -2 minus I? Hopefully you can see that. Actually, that's -2 plus I, and it is. That's what I have written there. So, okay, that is tricky. We need to find a way to reduce that matrix, and as ugly as it looks, yeah, it looks ugly. It's not as bad as you think, because if we use the row operation, 2 minus I over 5 times row 1, we can turn 2 minus I times 2 plus I, of course, is 5. And when we divide by 5, it comes out to be 1, and we get a nice 1 in the northwest corner, which is always a happy thing. But then we also want to take our 2 minus I over 5 and multiply it by this -1, so we get -2 minus I over 5 here, and 0 there. Now, we've got a nice fat 1 here. We can multiply this row by -5 and make a 0 here. So that's easily done. We got 1 negative of 2 minus I over 5 here, and a row of zeros in the bottom. Oh, that is a happy news. Now, it gets a little weird, because now we have to say, if we wanted to solve, we can't solve for K2, it's arbitrary, but K1 minus 2 minus I over 5 K2 equals 0, so K1 is 2 minus I over 5 times K2, and the eigenvector is K equals 2 minus I over 5 here and 1 here. But remember, any multiple of an eigenvector is also an eigenvector. And so let's take this eigenvector and multiply it by 2 plus I.
I think he's brilliant.
Well, yeah, why would we want to do that? Well, look how much nicer this is. No fractions. 1 here, 2 plus I there. Isn't that good?
Don't get technical with me.
Well, sorry, I didn't mean to get too technical, but let's get into this. Remember, the constant's going to be absorbed by the C1 anyway, so let's not worry too much about it. So, by the theorem above, that once we get one eigenvalue and eigenvector, the other one is just going to be the conjugate. So that means we ought to be able to somehow get into this in a very nice way. And so we shall.
I don't know what all this trouble is about, but I'm sure it must be your fault.
Well, maybe it is, but from our theorem, we can say we now have C1 times eigenvector that we just found times e to the -1 minus I t, and then plus C2 times the conjugate of this eigenvector times e to the -1 plus I, that's the conjugate of -1 minus I, times t, and that indeed is our solution. Now, what's wrong with this solution? Well, it's got i's in it.
Don't get technical with me.
Yeah, but we don't want to have i's in it. We want real numbers. So we have to find some way to do that. And since we can see that this itself can be thought of as e to the negative t, that's the negative 1 times t, times e to the negative it, but that's cosine of negative t, plus I sine of negative t, and sine of negative t is negative sine of t, so you can probably see why this turns out to be the same as this. And for the conjugate, it's just the conjugate. From what we know about Maclaurin series, we should have all that down. So looking at just this vector, we can write it with real and imaginary part. See, e1 times e to the lambda t, 2 plus I times e to the lambda t, that's just taking this and multiplying it by each of these terms. And then e to the negative t factors out of that, so it's e to the negative t, and then this is e to the negative it, this is 2 times e to the negative it, and then plus I times e to the negative it, but I don't know if you see what nice thing there happens. It's e to the negative t times, look here, cosine t minus I sine of t, that's this. And then 2 times e to the negative it, and that's cosine 2 cosine t minus I sine of t, and then plus I times e to the negative it, so plus I times cosine of t minus I times the sine of t. Now, doesn't that seem complicated? But here's what happens now. x1 is e to the negative t, of course, from here, and then we're going to separate the real part and the imaginary part. The real part is cosine of t here, and for the second slot we'll have 2 cosine of t, and then be careful to notice that this I times this negative I is negative I squared, which is positive 1, times this sine of t, so plus sine of t. And then plus I that factors out of this, this, and this. We have plus I times negative sine, e times, don't forget to multiply through by this, but I times e to the negative t times negative sine of t, and then down in the basement we've got cosine of t minus 2, that's this 2 times I sine of t. So, and notice where the I is now, right? I is out in a place now where we can say the constant will absorb. The constant will absorb that I. So we've got our 2 linearly independent eigenvectors. Here they are, e to the negative t times cosine t, 2 cosine t plus sine t, and k2, e to the negative t times negative sine of t, cosine of t minus 2 sine of t, remembering that this I will be absorbed by the constant c2 when we look at that. By the way, just to show you that they are linearly independent, notice the Wronskian, which is going to be this times this. Well, let me see. Let's do this times this. I don't know if there we go. E to the negative 2t times cosine squared t minus 2 sine t cosine t, and then minus e to the negative 2t times oh, sorry, it's going to be plus because this is a negative. So plus e, actually that's not e to the 2t, that's going to be e to the 0, so it's going to be plus 2 cosine t, wait a minute, this was supposed to be negative t, my fault. So e to the negative 2t times sine squared of t, and then plus 2 cosine t sine t, and look, this one and this one cancel out. Cosine squared plus sine squared equals 1, so the whole thing is just e to the negative 2t, and of course that's never 0. So we've got 2 linearly independent solutions of the system, hence we have a fundamental set. Yes. So we've got a fundamental set, and it's not only fundamental, they are real values. Yeah, all right. So that's what we were trying for, and we've got it.